So we stopped here, right? So we want to I think we pointed out that the matching network, parasitics, etc. can be absorbed into the matching network. The biasing inductor can also be absorbed into the matching network. Okay. Any questions so far? Yes. Poor efficiency. What do you mean by poor efficiency? Efficiency was 50 ohms. Correct.
So in this, we are measuring the output power less than the 50 ohms, so that the power is more. Instead of 40 milliwatt, we want 150 milliwatt.
I don't understand what you mean by saying measuring. Maybe it's a language problem because I'm not understanding exactly what you're saying. We are basically reducing this 50 ohms down to something else, correct? So let me see if this is writing now. Okay. What is the effective RL for the circuit here? Whatever is seen as the input of the matching network, correct? So if you were to draw a signal picture, I'll just show it without CDB. Whatever RL is, correct? Okay. Corresponding to that, you will get some swing out here at this point, correct? Okay. Now, the maximum swing here is limited because of bias constraints. Therefore, you're getting more for the same amount of swing. You can get more power because RL is smaller, correct? So that much is true, but I don't see, we have not talked about efficiency so far. Huh? Output power is larger because RL is smaller.
Narrowband is like we are preferring narrowband to enhance the output.
This has nothing to do with, well, you can build, if you build a pi match or a T match, you can actually build a broadband matching network, right? You can decide the Q of this. You can choose to do a broadband PA also. But fundamentally, this was a low pass system which is being converted to a band pass system, that's all. Again, even that is not strictly true because this can be a low pass matching network. That is why I hesitate to say things like narrowband, wideband, band pass, things like that. You can build a low pass matching network if you want, correct? Without absorbing some of the components. It is being converted into a narrowband system because you have decided to absorb some of the components into the matching network. Okay, some of the things which are integral to the PA. Now, therefore, it is no longer a, so for example, this infinite inductance, okay, was part of biasing of the PA. The PA itself was broadband. It is only the matching network that was making it narrowband. Now, the minute you pull in the matching network, part of the matching network into the PA itself fundamentally becomes narrowband, right? That's all I meant, nothing else. Does it answer your question? I hope it does. Okay. Any other questions about this? Okay. Now, let me see if we have. Okay. Very good. Since he brought up the efficiency question, now let's tackle that right now. If you were to define the efficiency of a power amplifier, how would you define it? Okay. So efficiency, power which is power delivered to load over okay. Of course, the power taken from VDD is a DC power, right? You're drawing DC current. VDD times I, if this is the bias current I, VDD times I is the denominator. The numerator is just P out. Okay, clearly if you were to plot this efficiency eta as we have defined it, right, as the swing is very low, the efficiency will be very low. As you keep increasing the swing, the output power will deliver to the load will also increase, until eventually what will happen? It will get very close to 100%. It will never be 100%, maybe 90% or something like that. Correct? In the saturated case. Correct? What is the maximum efficiency if you apply the constraint that the amplifier needs to be linear? How do you figure that out? Let us say VD-SAT is very small, can be neglected. Let us start with that. Let us, ideal case, VD-SAT is 0. Okay. Output DC is VDD. Okay. What is the maximum swing? VDD by 2. Correct. What is the maximum power delivered to the load? VDD square by 8 RL. Correct. Okay. What is the bias current that is required?
VDD by 2. Bias current is dependent on the base VG.
Yes, that is correct. So now you can see that the efficiency depends on the bias current. Now that's why I put off our earlier discussion to this, because we need to understand efficiency and how you define it. Now let us look at this carefully. So we said this is VDD times I. Okay, this is basically, well, it is the way I'm going to define it, it is basically, I'll just say V out squared over 2RL, where V out is the amplitude of the output signal. Let us define it like this first. And we want to find out eta max. So the reason this comes in is because you have 2 degrees of freedom for the transistor. Correct? You have the width of the transistor and you have the bias current. So far in all our analysis, we have never found one single thing that will help us set the bias current. Correct? How do you normally set the bias current of a transistor? Sure, current source and current mirror, but what I mean is the value. How do you normally choose? Huh? Normally it's gain and bandwidth, correct? Okay. Now in this particular case, of course the gain of the circuit will help you is one condition also, but it's a narrowband circuit. Now the minute you do all of this, it's a narrowband circuit. Even if it's a broadband, it's a low pass circuit, correct? Okay. So what will help you set I in this case? Not efficiency, no.
GM over ID, and depending on like if you want efficiency or linearity, you can bias it.
So far I have not said anything about linearity. I am assuming we are going to do this. I don't know if we'll have time to finish it in today's class. I think we'll probably need one more class. I think 3 hours is just not going to be enough to tackle everything, because even for linear power amplifiers, I have not been able to finish the topic. So most probably I will need one more class. But let us try to finish as much as we can today. Then we'll go to the other stuff. The point is, we have not touched linearity at all. Correct? So we don't even know. What I meant by linear PA is that the device should not cut off. The device should not go into triode. That is what we understand by linear PA. Okay. In fact, that is normally what anybody understands by linear PA. Let's be fair, right? Okay. So how will you choose the current and the voltage? No, because power handling capability is a second order concern normally, right? There are ways to improve it. There are ways to do a bad design based on power handling capability, but it's normally a second level constraint. So remember that so far you have used the triode condition. I asked you earlier whether you can use the cutoff condition. Correct? Can you use the cutoff condition here? What will the cutoff condition give you?
The cutoff condition will give you the input voltage. Like for example, if you give an input swing, the input swing can make the variance in such a way such that the device enters into the.
Okay, so remember what he said. So this is what we are trying to figure out. What is the maximum efficiency? So to do that, we don't know I, which is the I bias. So maybe I should just call it I bias to distinguish it. We are not able to set I bias, which is why we are going into this diversion, right? It's not a diversion, it's actually quite important. Okay, so what we are going to do, we're going to look at the cutoff condition. For M1, right? So as he pointed out, so what is the cutoff condition? The current, total current, I'll call it ID, okay, should, of course, should be greater than 0 for no cutoff, right? The current will not cut off if the drain current, total drain current is always greater than 0. If it just becomes 0, then the device will just cut off at one end of the cycle. At what end of the cycle will it happen? So let us now, I'm going to dispense with all this matching network business. I'm just going to do this. I need to set VB, I need to set the bias current, right? So remember, there are the 2 degrees of freedom for any transistor can be, for any device can be defined in various ways, right? They are all interrelated. If you are looking at the bias current, it's width and bias current. Normally that's the more common way of looking at it, more better way of looking at it in general. Width and I bias. The minute I bias and width are fixed, automatically the drain bias, sorry, the gate bias VB is fixed. You can also think of it as setting width and gate bias, in which case I bias is fixed, and so on. If you set VB and I bias, width is fixed, right? This is the more common way of looking at it. Okay, and you'll see in the reason in a minute why. Okay, so we'll look at these two. Okay, one condition I already know. The gain of the PA is one specification of the PA. I want a gain of 15 dB, right? That will automatically give me a condition because gain, the magnitude of the gain is GM times RL for this circuit. RL is 50 ohms or impedance matched version of 50 ohms. It could be 12.5 ohms, in which case you'd use 12.5 ohms here. Okay, but GM times RL sets the gain. If you know that the amplifier PA has to have a certain gain, it needs to have a certain GM. That helps you set, gives you one condition. Correct? What is the second condition that you need? So there is a second condition that you have already looked at, okay, but it is, you will see that it is not good enough. What is the second condition you have set? I'll go back. Note that you have already set a second condition using VD sat. You set that I wanted a certain P out, right? So let us say you work backwards. You wanted a P out of 40 milliwatts. Would you have been able to back calculate what VD sat 1 should be? Of course you would have been able to, right? You would have set P out max is 40 milliwatts. So what should the output maximum swing be? 1.6 volts, correct? And you would have said if it's 1.6 volts, it's biased at 1.8 volts, right? VDD. Then it can just touch 0.2 volts at the bottom. That should be exactly at the triode region. Okay, this will give you one condition. Of course, there's a second condition which relates the width and the current. The question is that good enough? Will it give you all the required conditions?
Now point 2 is the overdrain.
Correct.
So we know the overdrain.
Correct.
We know the maximum swing.
Okay.
So when the input swing is lower than 0.2, we go into cutoff.
Exactly. So the point is, suppose you set this, you have chosen the gain, you have chosen the VD sat, you come up with the current and width. correct? Excellent. Now if you do this, you build the device, build the PA, you may find that at the input you have Vin plus Vb going in here, correct? You may suddenly find that for part of the cycle the total voltage goes below Vt. It is possible, correct? It is definitely possible, depending on the value of gain and this thing. Will the device work properly? It won't. Okay, so remember, go back to your original analog circuits. The swing limit, there was a reason why you always chose the swing limit to be the minimum of the cutoff condition and the triode condition, because they are not limiting conditions. Okay, you have to choose the minimum of them to be the limiting condition. You could satisfy on one side, you could satisfy on the triode side and still cut off the device. You understand? Okay, so now we need to put in the cutoff condition. Okay, you calculate that also, the VDSAT also, you calculate the gain, but you need a third cutoff condition. How will you design this cutoff condition? You can still use approximate small signal analysis. What is the total current? GM times, you can call it V in, correct? Or I bias plus GM times sin omega t, correct? When sin omega t is -1, this will be I bias plus GM times V in. Is that correct? Correct, that's what I said. I bias minus GM V in. Okay, now the cutoff condition, where capital V in is the input amplitude. Okay, capital V in is the input signal amplitude. If this happens, okay, the device will just cut off. The point I'm trying to make is, you could satisfy the gain condition, okay, and the VDSAT condition if you chose a very small current and very large device. I hope you see that, because the condition you set, you can choose as large a device as you want. Fundamentally, theoretically, you could do that. You could choose a large device and a small current to get a minimum value of GM, okay, such that it satisfies the gain condition and also satisfies the VDSAT condition. Agree? I hope you see that. Okay, because let us say you did not meet the gain condition, you would choose a larger width so that it will get more GM, correct? What will it do to VDSAT? It will reduce VDSAT. You are anyway already meeting VDSAT condition, you will have a smaller VDSAT, you will still be meeting this output max power condition also, right? But you can see that if you were to choose a very small bias current, you would violate this condition. Okay, I hope you are able to connect up these variables now. Do all of you understand what I am trying to say? Excellent. Okay, so now you have a condition on the minimum I bias. Okay, now let us try to arrive at this in a different way, because I don't know V in. Maximum signal amplitude is not a fixed thing. Again, because remember, all the specs are not exact specs. What they will tell you is gain should be at least so much, right? Output power should be at least so much, and so on. Correct? You want to arrive at the best possible way. So the best possible way to design these things is to do it such that the triode limit and the cutoff limit is the same. That is what you want to do, so that they are not wildly off, so that you are limited by one much more than you're limited by the other. Correct? If you do that, normally that will be the optimum way. Let us say we do that here. I want to set I bias such that the triode limit is the same as the cutoff limit. How will you do this? We don't. which is why you should not tie it to the input swing. What else can you tie it to? Go to the circuit. When you are giving out, let us say that the two swing limits are the same. Let us look at that condition. That will help you figure out. So I am now saying set okay, I am going to do this first because this will give me somewhat optimum operation. Okay, because I am not having an over designed VDSAT, I am not having an over designed iBias. Okay, very good. How do I arrive at this condition for iBias if I set these two to be equal? Very simple. All I know is that, so remember, where does the signal current flow? The signal current cannot flow into the infinite inductor, it flows into RL, correct? So actually, so what is flowing into RL is, I'll call it small id, which is the signal current. Okay, there is no DC current through RL. What is flowing here? And this output voltage is VO. Okay, what I'm going to do, I'm going to set ID to be equal to what? First of all, I don't have to set ID to be equal to anything. It is just VO by RL. But what this helps me is, it helps me set a condition on ID, because I set this to, I'll set this to the triode limit. Okay, I can now get a condition on ID. Okay, and remember, that is exactly what this iBias cutoff limit is. You understand? I am now going to set iBias equal to VO by RL. What is VO by RL? What was VO max? This is what I mean. Exactly. Does everybody understand this route that we have taken? Okay. If I set iBias to be exactly equal to VDD minus VDSAT by RL, okay, if I do this, what will happen? The cutoff limit and triode limit will be equal. This condition is satisfied. Agree? Okay. Now what I have to do, I just have to go back. Now I have, using these two, I have already set both the iBias and the width of the transistor. Okay, because P out max sets the W now, sets VDSAT and that sets W. And iBias together. Okay, from P out max, I get the value of VDSAT. From the value of VDSAT, I work out iBias. The minute iBias is fixed, W is fixed. Okay, so this is what I get. Does it make sense to everybody? Now, note that I don't have control over the gain. What will you do? Let us say this gives you a lesser value of gain than what you wanted.
Cascode.
Absolute cascode will not help.
Cascode will improve gain.
It will not. It will not, because gain is just GM times RL. So cascode will not improve gain at all. Okay. Cascode can improve gain if you had a current source, no RL. In this case, cascode will not improve gain at all. What will you do if gain is not enough? So if I apply the condition that I'm going to set cutoff and triode limits are equal, it sets both width and W uniquely. Okay, to give me what conditions have I used? I have used the condition for P out max to set VDSAT. Okay, that together with this condition has set I bias and has set W. Agreed? Because it has set GM effectively. Okay, now the minute you set I bias and width, you have set GM. You have not GMRL is the gain. You have set the gain. The gain is too low. What can you do to improve the gain? Of course, you can only increase width or current. What are the effects of increasing width or current? Okay, parasitic capacitance will increase. That is right. Okay, that can be managed to some extent as long as you don't increase width randomly to a much larger value. You can absorb the as long as you are building a narrowband PA, parasitic capacitance can be absorbed into the matching network, right? What will you do? Of course, the only way to increase gain is to increase width or I bias or both, correct? Okay, look at the effects of increasing I bias. If you increase I bias, what is happening? Will your cutoff limit get better or worse? It will get better if you increase I bias. So you're moving further away from the cutoff limit. If you increase I bias, keeping the width the same, what happens to VDSAT? VD. If you increase current keeping width the same, what will happen to VDSAT? It will increase. Okay, so you're tampering with the triode limit. You can't do that. So you can't increase I bias because VDSAT, if it increases, P out max will be disturbed. Okay, so the best way to do this normally is to keep the current density in the device the same. You increase both current and width by the same number, same factor. So let us say I want twice the GM. I'm going to use twice the width and twice the current. Okay, VDSAT will not change. So P out max will not change. Only thing that will happen is that the current limit will get better. Triode limit will stay the same. The maximum power at all, but you have just increased the denominator. You understand? Any questions about this? So you are now taking a hit in efficiency because you don't have enough number of degrees of freedom. Okay, the number of degrees of freedom is only 2, right? It's I bias and W. You don't have any other degrees of freedom. RL is fixed 50 ohms, correct? Even if you were to able to match it down or up, basically the load resistance is fixed, right? You can match it down, in which case RL is smaller or larger. Okay, that will affect other things. But in the active portion of the circuit is width and I bias. You can only set 2 parameters. Okay, if you do this, if you want to get maximum efficiency, right, you can't get the same. If you want to get maximum efficiency and maximum P out at the same time, okay, you can only guarantee a certain amount of gain. That is a device limitation. You can do better by choosing a different device, not CMOS, but something else. You understand, right? If you had the choice of tinkering with mu n or mu p, clearly that can also be changed, which is what I mean by saying go to a better technology. Okay, any questions?
So from this we can conclude that on improvising the gain, our efficiency is so, like the thing is like efficiency and gain are like not closely integrated.
Not?
If we want good gain, then our efficiency will be bad. From this you can improve.
They are related. Okay. I wouldn't. The takeaway should not be that gain is bad or efficiency is good. That purely depends on the circuit. and the other specs clearly, right? If I wanted only lower P out, I can get both good gain and good efficiency at the same time, isn't it? So the constraint has been that I want a maximum P out max and maximum efficiency. That is what has led to, like I said it is a potential insufficient gain. I asked you what will you do if the gain was not good enough for you. That's all I said. I did not say it's bad gain. Okay. Okay.
In this case, the signal current that is flowing. In the cutoff scenario, that is equal to bias current.
Correct.
So, I mean, for a particular power, we will need that much signal current to flow. Doesn't matter what our P is.
Correct.
Then the efficiency should be higher.
Okay. So that is right. So what will happen if you want a certain output power, right? If you choose a lower I bias, you cannot choose a lower I bias than the signal current. Okay, that you cannot do, because definitely you will not be able to hit max power. So in some sense, the output power spec pretty much defines both the bias current, okay, as well as the well, I hesitate to go because it's a second order thing. It sets the bias current. Okay, I'll just close with that. The maximum output power that you need. See, in some sense, if I take this circuit, I could have started out like this. I could have started off with this condition. I started off saying it's VDD minus VDSAT by whole squared by 2 RL. Correct? I could have started off with this condition. I could have said P out is signal current squared RMS of signal current times RL. So let us say the peak value is ID, right? Maybe I shouldn't use this like this. I'll write it like this. It's ID squared RMS times RL, correct? It's a sinusoid. It doesn't cut off. Okay, I could have used this to set the bias current. So it needs at least a minimum bias current. So this can set the bias current also. Okay, a minimum bias current is needed, but this does not set the maximum bias current. I could choose a bias current larger than the value set by this and still meet the P out spec. Device will be further and further away from cutoff. Okay, if you plot the current waveforms and voltage waveforms, you will understand this. So let us say this was I bias. This is 0. Okay, I can set I bias such that at max swing it is like this. But if I move this down, it will get closer and closer to cutoff. I can choose anything larger than that minimum value. The P out will be defined by this amplitude.
Yeah, but if I bias is smaller, then efficiency is better.
Yes, but it is no longer a linear PA. Because you're cutting off.
No, cutting, and it is still like that tip is just touching 0.
Yes, the tip is just touching 0. The device just touches cutoff, right? It is still technically linear, right? The efficiency will be better in that case compared to a case where you choose a higher I bias. That is all I'm saying. That is what I said first also.
So that is the best thing you can do in efficiency.
As far as efficiency goes, that is the best thing you can do. If you want the maximum efficiency of a linear PA will happen when you use this to set I bias. You use this condition to set I bias. That will give you the maximum efficiency. That is absolutely correct. Okay. Now go back to this guy here. Under this condition, let us say you have chosen I bias like this. How will you choose this first? Let us come up with exact expressions for this. So okay, P out is, I said P out is ID RMS squared times RL. correct? Now let us not let the gain condition set us back. So let us say gain is a second order, is a second level spec. I want maximum efficiency and maximum P out, because remember, you can get more gain from the earlier stages and a lot less gain to the PA if you really need to do that. Okay, so I am more interested in P out. Okay, number one. Number two, since this is burning a lot of power, this is the one that is really the power stage. I want it to have good efficiency. So I am interested in P out max. Okay, and I am interested in eta max.
The previous stage itself is like very small, like we have a conversion mixer.
I can have, yeah, it can be a Gilbert mixer. I can get more gain from an active mixer, no? I can add a pre-driver stage, right? I can have a pre-power amplifier which will drive the input capacitance of this amplifier. It is not driving 50 ohms. The specific thing about this power amplifier is that it's driving a 50 ohm real load. There is a difference. Okay? I can have a pre-power amplifier which drives the input capacitive load of this guy. No problem. I know how to do that. Right? You have done LNAs and all drive capacitive loads, right? How will you do it? If you want to tune this thing, if you want a highly efficient circuit, you build a tuned amplifier. Common source amplifier with a tuned load will give you best enough gain. Okay, that is no problem at all. So I'm interested in these two. Okay, so then what will happen? How will I choose? Can somebody tell me? P out is ID RMS square times RL, correct? I'm interested in maximum P out and maximum zeta max, maximum efficiency. What should my design procedure be? I want both at the same time. My design, see, I need to set two things, width and current. Correct?
So we have numbers for P out max and eta max.
Okay.
So it's specified for this.
Yes. But I want to work it analytically. I'm not going to give you numbers. I want to work with symbols. How will you derive conditions for I bias and W? So P out max, you know, right? I'll say this is equal to P equal to zeta, right? So first thing, what will you do? Huh? Find the voltage swing. Okay, then.
Find VD sat.
Okay.
You know the VD sat. We set it such you set the current such that the swing we get maximum swing by choosing VD sat. Choosing an optimum VD sat, which fits both.
But cutoff and this thing. Okay, so I guess what will the equations look like? That's what I'm interested in. This is P max, correct? I'll call that some P.
So we can like have back calculate ID from this equation.
Okay.
From ID we can get we can use the GM and I bias equal to that cutoff equation.
Okay, I'll first do this, correct? P max, okay, is P is equal to VDD minus VD sat by 2 RL. Okay, so first of all, this will give me VD sat. Okay, that will give me a VD sat number. Okay, now I also know you'll get maximum efficiency if the device just cuts off at the same point where I'm not using too much bias current. I'm just using enough bias current such that when it hits the triode limit on the positive side, it will hit the cutoff limit on the negative side of the current, of course, right? Okay, so now how will I put that down in numbers? This is one equation. What is the second equation?
ID equal to GM
root 2? This one, this ID RMS or capital ID RMS, I don't understand. What is, I just wrote it down saying it's a RMS of the signal current. But RMS as a signal current is not an independent variable of its own. The independent variables are things like VDSAT, VDD, things like that. You can work backward. We just wrote this down. We just wrote down that. That's all. No. If I set I bias equal to VDD minus VDSat by RL, this will satisfy both conditions. Okay. This condition will satisfy both of them. Okay. So now I'm going to choose okay. I have gotten VDSat already. Now I choose this to set the bias current. Okay, and now this will set the what will this set? So VDSat is set here. So I bias is set. So these two put together, W is set. Okay. Now this will give me maximum power that I wanted. Now the only thing I need to find out is what is this eta max? Eta max, correct? What this is the maximum efficiency case. Okay, you cannot get better efficiency than this. The device is just cutting off. If I reduce the current in it, so remember the efficiency can be improved if you improve the numerator or increase the numerator or decrease the denominator. Okay, increasing the numerator means you need to increase P max. That can only be done till a certain level, because as you keep decreasing VDSat, right, you're not going to get like grossly different, because VDSat can decrease from 200 to 150 and so on. Eventually the device will no longer be square law. There is no use decreasing VDSat anymore. You understand? There is an upper limit on P out that you can get, which is set by VDD and RL. Okay. At that point only you can choose just barely minimum I bias, which sets a denominator also. Does it make sense? Okay. In fact, if VDSat was small enough, you can see that I could have written these equations saying, let us say VDSat is much smaller than VDD, less than 1/10 of VDD. Okay, VDSat can be easily be 100 millivolts, right, and so on. Power supply is 1.2 volts. So let us even neglect VDD for a first level hand calculations. Okay, if you neglect VDSat, what is PO max? Is VDD squared by 2RL. Correct? PO max is VDD squared by 2RL. What is I bias? VDD by RL. Okay. Does it make sense? Okay. I am now choosing a large enough. I am independently assuming. Okay. But I am going to make this approximation to calculate eta only. Obviously, I still need to know VDSat to calculate W. Okay. That's all I am assuming. Okay. Now, how can I calculate? What is this? Okay, I bias calculated at PO max. Correct? Huh? So it's VDD squared by 2RL by VDD by RL times VDD. Okay, so this is basically half, 50%. Does it make sense? You can get if you apply these two conditions, you can get approximately a 50% efficiency in linear operation. Okay. How many of you have looked at power amplifiers at low frequencies like audio amplifiers and so on? Anybody remembers that? No, class A amplifiers using, let's say, bipolar transistors, MOSFETs also, but you're going to drive, you must have studied in your undergrad, many of you. Do you remember what the peak efficiency was for linear operation? For class A it was 25%. Why was that? Why are we by the way, we have not done class A, class AB, class B. Do you know all of that? Not sure, right? I'll cover it in the next class. Okay, but class A operation is defined as not cutting off, not going into triode. That is class A operation, which is what we have been looking at in today's class. Okay, if you do like that, okay, for low frequency amplifiers, you get an efficiency maximum class A efficiency of 25%. We are getting 50%. Why is that? People who have done this before. Why are we suddenly getting this? Is also class A. It's because of the inductive load. At low frequencies, if you study generalized power amplifiers, you normally assume you don't have an inductive load. You can have a resistive load, you can have a current source load and so on, but not inductive load. So the bias point is normally assumed to be VDD by 2. Whereas our bias point is VDD, you can have a larger swing, okay? All of that goes into the improving efficiency. Okay, so now here is my next question for you. Suppose I had the option of increasing VDD. Can I increase efficiency beyond 50%? Can I? I can't. Okay, if I want linear operation, you can see that it's more or less independent of VDD. It's independent of RL also. Okay, so this is the maximum efficiency you can get. You normally get, if you want linear operation, you'll get slightly lower than this. Okay, very good. I think I'll stop here. It's already 4:40. I'll stop here. I think we need to have one more class because there are a lot of loose ends. We have not done other classes of PAs. We have not even done an example design and so on. Okay, so I'll have one more class sometime this week, and then we'll try to wrap it up during that class.